In the past few segments, we've been looking at how to understand weak acids, weak bases, and the perturbations that can happen when a strong acid or base is added in. Right now, I want to look at this challenge problem to see some of the common pitfalls that people can run into and how to approach these sorts of problems. So I recommend right now that you pause the video, try this problem for yourself, and check to see how you do. Please only unpause the video when you have either found the solution or feel like you've gotten stuck and can't continue any farther. Okay, so when you're starting to solve a problem like this one, it's almost always the right choice to begin by writing out the chemical reaction equation. In this case, we're going to be reacting our aqueous HCl with aqueous ammonia, and we're going to be producing ammonium and chloride. Now, if our goal is to determine the pH, we can pretty quickly decide to neglect that chloride. It's a base so weak that it's not even a base. But this is definitely a case where you want to sort of feel your danger sense tingling, because we are consuming a weak base to produce some weak acid. So depending on exactly how much is made, we could really be dealing with a variety of situations here. We could have added such a small amount of HCl that what we mostly have floating around in solution is weak base. We could have added a fairly close amount such that we have similar amounts of NH4 plus and NH3. That would mean we're dealing with a buffer. We might have added just enough of our HCl to consume all of the NH3 into NH4 plus. There we go, that looks better. In which case we'd be dealing with a weak acid. Or we might have added so much of our acid that we've just quite simply consumed all of our base and now be dealing with a strong acid. So to approach this problem, we are going to need to figure out how many moles of each we have. To do that, we'll multiply our 10 milliliters. For every 1,000 milliliters, we get 1 liter. And for every 1 liter, we get 0.025 moles. That's going to wind up equaling 2.5 times 10 to the negative 4 moles of NH3. We likewise will have to do an equivalent calculation with our HCl. And this is a point where things may be starting to look a little bit serious to you. That is, we have quite a lot more HCl than we have NH3. But these amounts are still close enough together that a meaningful amount of the HCl is going to be consumed. Let's do an ice table to demonstrate how that would be done. So we initially had 5 times 10 to the negative 3, 2.5 times 10 to the negative 4, 0, and 0. We're going to be reacting these in a 1-to-1 ratio, meaning that we're going to react away, in this case, all of our NH3. and sum of our HCl. This number is going to be 4 point, technically, if we want to get fancy, 75. But keep in mind with significant figures, this place is equivalent to this place, 10 to the negative 3, 10 to the negative 4, which means we're going to need to round this to 4.8 times 10 to the negative 3 HCl. No ammonia remaining. We will have produced some ammonium and chloride, so those are the moles of stuff floating around now at equilibrium. So with that in mind, which of these situations did we wind up in? Yeah, we're in the strong acid case. That is, even though there is some amount of ammonium present, that ammonium is a weak acid. By comparison, we have 20 times more strong acid. So that means that this strong acid, HCl, is what is really controlling our pH. So things are going pretty well, but how do we find our pH? Well, you just take the negative log base 10 of that, right? Hold on. We're talking about a case where we were adding together significant volumes of each. So our new volume is now 15 milliliters. So if we put our new number of moles of HCl, which will thus be the same number of moles of H+ that are floating around, double check for yourself that you feel comfortable doing the conversion between milliliters and liters here. That should give us an answer of 0.27 molar H+. But in this case, the concentration actually went down by more because we were diluting the HCl. So what is the pH here? Well, you can take the negative log base 10 of this number, which should give us a pH equal to 0.56.